IVM.
Science journalists Nandita Jairaj and Ashima Dogra have traveled to institutes across India, interviewing a wide spectrum of women in science and discovering research that is pushing the boundaries of their respective fields. Through the course of these podcasts, we will learn of the daily grind that makes up their lives as scientists, the significance of their research, the limitations of their experiments, and the challenges and discrimination they encounter being women in the scientific community. In this podcast, Nandita talks to Indumathi D, a particle physicist.
I like science. I was not deeply committed to science or very keen on science. I just came into science very accidentally. In fact, to be very honest, it was the last thing on my mind. I used to play cricket and I did a master's just so I could stay on the university cricket team.
Okay.
But then
was in Chennai?
It was in Chennai. I was in Madras Christian College at that time.
You were just listening to Dr. Indumathi, a particle physicist I met up with last year at the Institute of Mathematical Sciences in Chennai. The past few years in particle physics have been super exciting, not just for the scientists, but also for the general public. We've all heard about gravitational waves and the quote-unquote God particle. If you're a bit of a science enthusiast, you may recall an episode in 2011 when it was reported that neutrinos were found to be traveling faster than light. This was pretty incredible because for 100 years, we had taken for granted Einstein's prediction that no object can travel faster than the speed of light. The violation of this rule was described by one physicist as an atom bomb in the heart of our understanding of the universe, and popular media was abuzz with the possibility of time travel. Of course, it only took a few months for these hopes to be dashed. It was just a mistaken calculation. The whole episode was a sign of how little we know about the elementary particles called neutrinos. And this is what makes them a fascinating area of study for particle physicists like Indumathi.
Neutrinos are also fundamental particles like electrons, but they don't sit inside the atom, so they don't make up matter as we know it. But the main thing is that neutrinos don't have charge. They don't have electric charge. So the way they interact is through something called weak interactions. Okay. So to understand it, so for every, so in fact you can understand, I've said now strong interactions, weak interactions, and electric interactions, or also electromagnetic interactions are the same. So if you look at, on the scale of interactions, suppose I say that I have one weak interaction. So suppose a particle can have all three interactions, right? Okay. So every time a particle experiences a weak interaction, it would have experienced 1,000 electromagnetic interactions and 100,000 strong interactions. So that's why strong interactions are called strong. So just the rates of interactions or the probability of interaction is much, much higher with strong interactions. So in other words, every time I have one electromagnetic interaction, I will only have a 1 in 10,000 possibility of having a weak interaction. Right? That's why they're called weak. They are very, very weakly interacting particles. They don't have strong interactions because they don't sit in the nucleus of atoms, and they don't have electric charge, so they don't experience electromagnetic interactions. But all particles in nature will experience weak interactions. So that's the only interaction they have, weak interactions. Because they are so weakly interacting, they practically pass through anything unobserved. So they don't see, what do you mean by interacting? I see something because some light is, even though it's transparent, this bottle, part of the light is getting reflected back into my eye, right? So it's getting scattered back. Right. But if it's not interacting, it will simply go through.
Right. Then it would be invisible.
Yeah, it's invisible, but nearly invisible because it does have some interactions, right? So the thing is, so for example, the most copious producers of neutrinos in our environment is the sun.
Right.
So the sun produces like 40 billion neutrinos per square centimeter per second. That means through my thumb, if I just roll out my thumb, so as I just click once, 40 billion have gone through. So it's not a number that's even for a scientist easy to understand. They're just huge. The rates or the amounts. So when something is sitting here, you call it the density. When it's moving, it's called a flux. Right? So the flux of these neutrinos is really huge. So the other source of neutrinos that you see naturally in the whole universe, in fact, is coming from what are called cosmic rays. So cosmic rays are mostly protons, but they come from all parts of the universe. And the origin of these cosmic rays is an open problem in particle physics. We don't really know.
But they do enter the atmosphere.
They enter the atmosphere, and when they hit the Earth's atmosphere, because there's so many molecules, right? There's nitrogen, there's oxygen, there's so much stuff. They hit those molecules and they produce a lot of hadrons. I talked about hadrons. Pions are the most common hadrons. And these hadrons decay, and in the decay chain, neutrinos are produced. So these are called atmospheric neutrinos because they produce in Earth's atmosphere. So what we want to study in INO is actually these atmospheric neutrinos.
So how do you study a particle that's practically massless, chargeless, and rarely interacts with matter? Simple. Turns out all you need is a 50,000-ton magnetized iron structure kept 1 kilometer deep underground and embedded with 30,000 glass detectors. And that's pretty much what the India-based Neutrino Observatory, or the INO, is. Once constructed, the INO will be a giant laboratory that will allow Indian particle physicists to design and carry out neutrino experiments inside it. But why do you need such a large detector, and why does it need to be so deep?
The thing we're doing is, the reason we build anything underground is that if I make a detector on the Earth's surface, there's a huge number of charged particles in the cosmic rays. Now, what I want to do is that there are many kinds of neutrinos. The particular kind of neutrino we want to study is called the muon type of neutrino. And when it interacts with matter in the detector, it will produce charged particles called muons. The muons are like heavy electrons. So in fact, if it just is convenient for you, you can think of them as just electrons, heavy electrons. Now, such muons are actually produced when cosmic rays hit the Earth's atmosphere. So if I have a detector on the surface, I won't know whether I'm measuring the neutrinos which have interacted with the detector to produce the muons or directly the cosmic ray muons. Now you can say, okay, if the background is small, we can take care of it. But actually, it will turn out that we are going to have a really massive detector. I can tell you more details about it later. In this massive detector, we expect about 3 events per day. That is, I would expect to find 3 muons per day in this detector because of neutrino interactions. But in this detector, when placed 1 kilometer underground, I will get something like 300 events per hour from cosmic ray muons. And that is like 1 kilometer underground. So if I put that on the surface, I will probably have something like 10 billion muons coming from the cosmic rays. So it's not even a needle in the haystack. It's like needle in several billions of haystacks. Right? So there's no way you can do these neutrino experiments overground. So the only reason you want to go underground is because you want to cut down the background so that your signal is much clearer than the background.
So how deep?
So 1 kilometer is something that we can do feasible. So it's a compromise between the physics and the engineering. Much deeper than 1 kilometer is very hard to go to because the rock becomes very, the pressures there become very high, rock pressure becomes very high. And less than 1 kilometer, the background is too high. Even now we are going to be 3 neutrino events a day versus 300 muon background per hour. So it's still tough, but we can do it actually. With the electronics and kind of modern day technology, there is no difficulty in doing it. So that's no problem. So now I have to distinguish between the naturally produced muons, which are huge in number, and the muons which are produced because neutrinos are interacting with my detector.
So there's no way to detect the neutrinos itself.
This is the way you detect neutrinos, right?
So if it doesn't, non-interacting neutrinos cannot be detected.
No, cannot be detected. So they have to interact and produce something. So it's like this, like what has happened is that this light has fallen on the bottle and the energy has fallen on my retina, and that's the little pulse that is going into my brain. Right? Something has to be there. So that pulse is not the same as the light or the bottle. I mean, pieces of bottle are not going inside me. So the neutrino is always detected by detecting something that it produces. But most often it produces these muons. It can produce other things, but it's the cleanest signal. So when you produce a muon, then I want to know that for sure this came from a neutrino and not generally from the cosmic ray background. Okay, so the main reason we want to go underground is to clean out this background. But of course that has been misinterpreted because you want to go underground, you want to hide things there. That's what people believe. So we want to have a drive-in and drive. So now it comes to the size of the detector, right? We want to build something which is 50,000 tons of iron. Okay, so that will be something
like a chamber.
So the size is the size of this building, 5 stories high. So that's the kind of detector you're thinking of. So it's like a 5-story building, and it'll be roughly the size of a typical Indian airport. Actually, it'll be huge. It's just the detector is calibrated so that every 3 centimeters of it has electronics, so you can detect signals in a 3 centimeter by 3 centimeter.
So basically, the bigger it is, the more you have chance of
interacting. Perfect, exactly. That's right. That's why you want it, because neutrinos are weakly interacting. I can't do a tabletop experiment with neutrinos because of that. because by the time, another way to understand it is that if you line up 7 Earths, a neutrino can go through all of them without interacting even once. Or another way of looking at it is that all those billions of neutrinos may not even have one interaction with you in your lifetime. So they're really, really weakly interacting. So to increase the chances of interaction, I must have as large a detector as possible. Right? So that is the thing, key thing about neutrinos. So that's what we do. So the neutrinos come in and produce charged particles. These charged particles are easy to detect with any electrons. Then what we do is that we magnetize this detector. That's why we want to use iron.
Okay.
So if I produce muons, we know that charged particles bend in a magnetic field.
Okay.
But if I have anti-muons, which can be produced by anti-neutrinos, they will bend in the other way.
Okay.
So that means by looking at the bending, I know whether I got a neutrino interaction or an anti-neutrino interaction. And in fact, the physics that we want to do looks at the difference between the interactions of neutrinos and anti-neutrinos.
Okay.
And that's the physics we want to capture.
So if the INO is set up, what kind of discoveries are possible? And could these have applications?
Right now, it's a basic sciences project. We really only want to understand the properties of neutrinos. Already there have been more than half a dozen experiments in the world which show that neutrinos have very, very exotic properties. One of the simplest things that is easy to explain is that people thought neutrinos were massless. They turn out to have a mass. So that is extremely easy for people to understand. Something is massive instead of being massless. The other property is a little more subtle. I told you there are many types of neutrinos. So I said electron and a heavy electron called muon. There's an even heavier electron called the tau.
So are these the flavors?
Yeah, these are the flavors. Okay. Now, these 3 charged particles are very different from each other because their masses are different.
Okay.
Because their masses are different, their interactions are different, and I can very easily tell them apart in a detector.
Okay.
But associated with each of these 3 particles is a neutrino. So associated with the electron is the electron neutrino.
Okay.
With the muon is the muon neutrino.
Okay.
With the tau is the tau neutrino.
Okay.
Now think about it. I have 3 different flavors and they're practically massless. How do I know which is which? So this is a question. Are they the same? Are they different? In what property in this flavor? What is this flavor property that distinguishes them? So this is the kind of thing that INO really wants to focus on. It is basic sciences. So at one level, here is a particle we don't know much about. In fact, here are particles we don't know much about. And they have these strange quantum mechanical mixtures. So we know that quantum mechanics is important at the subatomic level. But here is something where quantum mechanics is essential to understand their behavior.
Right.
Whereas electrons, muons are all distinguishable. They don't mix at all. Right? So why is it that the two which are related to each other in some way are actually behaving completely differently? Can you write theories of these things? So just at one level, just to understand these particles which exist and why do they behave that way.
Right.
The other thing is that even a small mass of the neutrino has tremendous consequences for cosmology because we know that they will add to the mass of the universe because there are so many of them. So all the calculations that have been done, see, the mass of the universe drives the density of the universe, which tells you whether at what rate the universe is expanding. We know that we have an expanding universe. Now all your density calculations are going to change because you have this component which you thought was massless, but very, very large in number. So even if each of them has a tiny mass, it's going to make a huge difference to the contribution that it makes to the universe itself. So to know the mass itself, and it's completely unknown today. We just know that they are massive. We don't know what value it is. So it's a very important consequence for cosmology itself.
Right.
So all these are arguments towards the basic sciences. The other argument that many people make is even though neutrinos are very weakly interacting, let's take the analogous case of electrons. About 100 years ago, we just discovered electrons, right? Why did people discover electrons? What is the use of it, right? There was no use of it at the time. It was just driven by human curiosity. But today, you're recording my conversation because of electrons, right? The whole field of electronics. So I think that the way science feeds into technology is something we don't understand. And a component of funding or support for basic sciences is absolutely crucial because these are what lead to applications in technology, and the world is driven by technology today. Whether you like it or not, it is. Okay. So a concrete example that I would like to give is that you've heard of PET scans, right? PET scan is actually originally a particle physics detector. Okay, so it has come
an unintended consequence of
not unintended. People realize that, and actually some of the particle physics students moved into industry trying to make this instrument. Okay. So the neutrinos themselves may not be of use, maybe even in the next 100 years. But the detectors that we are making, very, very sophisticated detectors, may actually have use maybe in medical imaging like PET scans, or may have use in some industry, whatever, we don't know what it is. Okay, so the neutrino physics itself, as I said, may not have applications, but the sophisticated technology that we are building around it surely will have. Because ultimately this technology is detecting electrons and muons, which are charged particles, not original neutrinos, right? So that technology can have a lot of applications. So I think that it's important to support. And I know every number about INO is humongous. I mean, apart from being 50,000 tons in weight, the active detectors that will detect these charged particles, we have to build 30,000 of them. No, it's not something that can be built by 2 labs in India. We have to have an industry interface. Anything that you talk about, we need 4 million channels of electronics to pick up the signals coming from these RTCs. 4 million chips are not something that 1 or 2 or even 10 labs in India are going to build. Again, you have to go to the electronics industry. And this is already happening actually. A lot of industries, in fact, because our RPCs are made of glass, Saint-Gobain has been working with us.
RPC?
The active detectors.
Okay.
Stands for resistive plate chamber.
Okay.
But basically it's made of glass. So the active element that actually detects that a charged particle has gone through, a muon has been produced, is called an RPC. That the R&D has been done for it in India, and they've been manufactured in India. And Saint-Gobain is very famous for its glass. But now they're using their glass to make the RPCs based on input given by us. But very, very honestly, at the basic level, it's just driven by human curiosity, I think, to know what it is.
It would seem that the sole purpose of the INO is to study neutrinos, but there's a lot more to it.
So I've done a lot of non-INO neutrino physics, but I think the main reason many of us felt very strongly about, the reason we wanted to build INO in India is that you want to have a lab, a large enough lab, so it showcases some very good quality physics, and can be a generic lab. You don't want to just make one experiment there. You want to make it a lab which can have many different kinds of experiments. Exactly like CERN is a facility, or LHC is just one experiment in CERN, right? I mean, there are so many other experiments in CERN. Or in Fermilab, there are so many experiments, not just the Tevatron. So you want to have a lab where you can have many experiments. But the different thing is that once you have it in India, you're going to drive the experiment yourself. So the physics goals are set by you. Now, when you join a collaboration abroad, and India, even though it has presence, very strong presence in many labs abroad, you're not determining the physics. You're not determining the direction that these, the choices of experiments or what kind of physics they want to study. Very few people in India are at that level of decision making in those labs. For obvious reasons, right? Because you're not the main part of the experiment. So what we wanted to do was to build something in-house. One reason is that the kind of physics that we do, phenomenology, is actually a very experimental related science. So you don't want to always, when you're writing theories for experiments that have been done outside, you never get the edge, right? Because the data is always not accessed to you or accessible to you immediately. Whereas if it's your own homegrown experiment, then you will know exactly what's happening, right? So many theorists want to do or have a lab in India because then they get first go at the data.
Right.
For me, it's not that serious to get first go at the data, but as I said, more to kind of drive the science itself. What kind of experiment you want to build? What is it that you want to measure?
Plans for the INO emerged more than 15 years ago. After a decade of ups and downs, it was looking like the project would finally take off in 2015 with the Union Cabinet's financial sanction of Rs 1,500 crore. But the joy of scientists like Indu was short-lived. Just 15 days later, Tamil Nadu politician Vaiko filed a writ petition against it, saying that the INO would bring unimaginable and terrible disaster to mankind and the environment.
So right now it's sitting in court. There are 2 different cases against it. One in the Madurai bench of Madras High Court
by Mr. Vaiko. At
Teni. Just in Teni, there's a place called Pottipuram, which is actually the Kerala-Tamil Nadu border. So even though we got all our local clearances in 2010, we didn't get financial sanction from the government of India. And actually Manmohan Singh, I think in 2012 and 2013 in the Indian Science Congress, he announced that INO will be funded, but he never moved the papers actually. So it was only when the new Modi government came into being, and so end of 2015 December 2015 is when it was sanctioned. I think the letter came in 2016 January. So those 3 years or something that we just waited. There was no money for anything at all. We weren't sure the project was on. And that was very bad for us. I think in that time, we just thought everything is fine, we're just waiting for the money, locals are fine, there was no environmental protest, nothing. So we were consolidating a lot of the physics at that time. So when we got the financial sanction, at that time we had to apply for air and water clearance with the Pollution Control Board. Okay. So then when the judge learned that we have not yet got the air and water clearance, he said, see, this is a very technical project, I don't understand all the details. So anyway, the state government is going to look at it because of the air and water pollution clearance. I mean, they will be able to tell whether or not, you will contaminate, because that's what he was saying, you will contaminate the water, you will contaminate the land. So the PCB is the right technical body to give the decision, and if it gives its clearance, then we will go ahead. Until then, you can't do any work. So he gave essentially a stay at that time. After that, the PCB has not moved the papers. It's now nearly 1.5 years. So, I mean, unofficially we heard that they were waiting for the elections to be finished. But now elections are finished and still nothing is moving, maybe.
But if they had, if not for these...
they would have easily given us the... Because in fact, the land in Teni was given free of cost by the Tamil Nadu government. In fact, by Ms. Jayalalitha when she was there, right, in the CMS, the previous 5-year term. So we don't see, we are not able to understand why this goes slow.
Being a woman in science, I asked Indumathi what she thought of the infamous gender gap.
His career is extremely unforgiving. You cannot... I know only one colleague of mine, in fact, this person who called his wife, who had 2 children, quit physics, quit means went slow and then came back and actually got a faculty position.
You're saying it's more difficult in physics than other subjects?
I think it's difficult in every subject. This gender issue we never talked about at all. I've been to, we have these schools where they teach advanced subjects in particle physics, and I've been to schools where, in one school in particular, I actually shared accommodation with the teacher. Because we were the only 2 women in the entire time. She was the only woman teacher and I was the only woman student, and we shared the accommodation. So from those times to now, when we have actually quite a significant fraction of women, both in the faculty and among students, I think we've really changed a lot. In my career, I have not experienced any gender discrimination. And I do not think that within the particle physics community, I am not aware really.
But you are a minority, right?
We are a minority, but we are not such a significant minority. If you go to Europe, in fact, in Germany, in the 2 years of my postdoc, I was the only woman student, postdoc or faculty member of that department. The only women were the secretaries of the department. So it's very, very bad out there. So compared to that, we are doing a lot better in India, actually. I'm only talking about particle physics. I don't know really about, not even particle, theoretical physics. Condensed matter like one is there. So we are kind of small, but not insignificant. So that's a very good thing. I feel that in India the problems are different. The gender inequality comes from social pressures. The woman is expected to do the housework, right? She's not able to cope. How can you cope with PhD and research is not a 9-to-5 job. You are thinking about the problem at home. If you have to look after the children, if you have to do the housework, if you have to do everything and then come and work, I don't think it's possible to do a good job of either. So I've been lucky in the sense that with my husband and I, we share everything, starting from the cooking, the cleaning, the washing, everything. So it's always been that kind of equation. So even then it's been hard, right? With 2 children, it's hard. But so in that sense, I don't think that the community itself discriminates against women. But you can see the dropout rate, right? Once they finish their PhD, the moment they get married, then there's this attrition rate. And the moment they have a child, then there's this huge attrition rate. They're simply not able to cope. So
that was science journalist Nandita Jayaraj in conversation with particle physicist Indumathi D. To find out more about her and other women scientists around the country, do check out thelifeofscience.com for Nandita and Ashima's work.
Good evening, ladies and gentlemen. This is your captain speaking. Sorry to say, but there's been a slight delay due to the apocalypse having suddenly begun. As you can see, there's death, destruction, and chaos taking place all around us. But don't you worry, food and drinks will be served shortly, and I would recommend checking out IVM Podcasts to get some of your favorite Indian podcasts. We'll keep you going till this whole thing blows over. Thank you.